Welcome to the introduction to FHEVM. This technology, pioneered by Zama, stands for Fully Homomorphic Encryption Virtual Machine. It enables us to run confidential smart contracts that perform computation directly on encrypted data, such as uint32 and EBOL, without ever exposing the underlying information. We are now going to demonstrate this breakthrough capability by building our private number guessing. Zama is a pioneering open-source cryptography company that has developed the world's most advanced fully homomorphic encryption (FHE) solutions for blockchain and AI applications. At its core, Zama has created the Confidential Blockchain Protocol, a cross-chain infrastructure that enables confidential smart contracts on any Layer 1 or Layer 2 blockchain without requiring modifications to the underlying chain. The FHEVM, Fully Homomorphic Encryption Virtual Machine, is Zama's core framework that enables confidential smart contracts on EVM-compatible blockchains. It enables confidential smart contracts on EVM-compatible blockchains by leveraging fully homomorphic encryption, FHE, allowing encrypted data to be processed directly on-chain. The key feature, it extends standard solidity with new encrypted data types booleans, EBOL signed integers, uint8, uint16, uint256, etc. signed integers, ain't8, ain't16, ain't256, etc. addresses, address. We will be building a private number guessing game. Here's how our confidential game works. The user first inputs their guess, and we encrypt it locally into an uint ciphertext. This ciphertext is sent to the FHEVM, where the confidential computation is performed. In a traditional game, all data is public, making it easy for anyone to front-run the transaction and cheat. Private game ensures all data is private and secured using FHE. If you're looking to start building with Zama's fully homomorphic encryption, the FHEVM React template is the absolute fastest way to go from zero to a functioning decentralized application. It's designed to be your one-stop shop for confidential development. To begin, we use git bash to clone the repository from GitHub, git clone, repository URL. This gives us a complete development stack right out of the box. Once cloned, we jump inside the folder and run npm install. This single command sets up everything you need. It includes Hardhat for our development environment, Ethers for standard blockchain interaction, and, most importantly, the FHEVM SDK, which handles all the complex cryptographic operations for us. Finally, we are ready to launch. You'll run the Hardhat node in one terminal to simulate the FHEVM environment and the React app in another. The beauty of this template is that it provides a fully wired-up frontend, our guessing game UI, that is already configured to perform the three critical steps of FHE development: encryption, confidential computation, and decryption. This allows you to skip boilerplate setup and focus entirely on writing your private Solidity logic. It truly is the best starting point for any developer looking to explore the cutting edge of confidential dApps. With the template successfully set up, the real work begins. Our focus shifts to the contracts folder, where we write our Solidity logic using FHE-enabled types like uint32. Crucially, we use the included Hardhat tasks to compile and deploy our contract on the local FHEVM node. After perfecting our confidential Solidity contract, the next crucial step is deployment. This is handled by the deploy.ts script, a standard component of the Hardhat framework. This script's main job is simple: to take our compiled private guessing game contract and securely place it onto our local FHEVM node. This local setup allows for fast, iterative testing and debugging. If we were ready for the public, this same script is easily configured to target the Zama-powered Sepolia testnet. Inside the function, we first grab our deployment accounts and the utility functions from Hardhat. We define our contract name as private guessing game. The core action happens with await deploy contract name from deployer log true. This single, powerful line sends the transaction to the network, creates the contract instance, and returns the crucial deployed address. Immediately after deployment, we log the new contract address, along with the chain ID and chain name. Logging this information is vital for us to track the contract and ensure our front end is always connected to the correct FHE environment, preventing any connection integrity issues. But the most important part for our full-stack application is the call to post-deploy. This specialized utility performs a necessary handshake between the blockchain environment and our React frontend. Instead of us having to manually copy and paste configuration data, this command automatically generates two essential TypeScript files, one containing the contract ABI, which tells our frontend how to talk to the contract-specific functions, and another containing the contract addresses, telling the frontend where the contract lives on any given network, like Sepolia or our local machine. Our final step before testing the game involves setting up the development environment, which requires running 3 commands simultaneously in separate Git bash terminals. This is the official Zama setup for deploying and running FHE applications. In the first terminal, we start the FHEVM blockchain environment with npm run hardhat node. This initiates a private, local FHE-enabled chain on port 8545. We use this node for rapid development and testing before touching public networks. In the second terminal, we begin the process of deploying our game contract. Since the goal is to target a public network, we run npm run deploy Sepolia. This command compiles our Solidity, signs the transaction, and pushes the private guessing game contract to Zama's public FHEVM Sepolia network. Once deployed, the contract is ready for interaction. The third terminal is reserved for running the client application, but since we haven't built the frontend yet, this terminal will be ready for the npm run dev mock command as soon as the React code is completed. Once deployment is complete, we open MetaMask, ensure we are connected to the Sepolia testnet, and the frontend will automatically detect the deployed contract. This deployment flow ensures that whether we use the local node or the public Sepolia network, our confidential game contract is correctly initialized. After successful deployment, the post-deploy utility automatically generated this file, the contract ABI. The application binary interface is essentially the translator. It shows the React frontend exactly what public functions exist in our smart contract, like setSecret and getHint, and what data types they expect. Since our contract uses FHE types, the ABI includes the specific structures needed to handle our encrypted data. This file, usePrivateGuessingGame.tsx, is the brain of our frontend. All codes can be found in the GitHub repo, link in description. It's a custom React hook that abstracts away all the complexity of communicating with the FHEVM. At the top, we import the ABI and address files generated during deployment, ensuring we know what functions to call and where the contract lives. This hook manages all necessary states, such as whether the game is active, who the owner is, and, crucially, the encrypted handles for the hints. Let's look at the 3 core FHE functions here. Set secret. When the owner sets a secret, this function uses the FHEVM React instance to encrypt the plaintext number locally in the browser. It then passes the resulting ciphertext and its proof to the setSecretSolidity function. getHint. When a player guesses, the guess is also encrypted locally. This function calls the contract, which performs the confidential computation, the FHE.EQ and FHE.GT comparisons, and returns the encrypted hint handles. These handles are then stored in our React state. Decrypt hint. It uses the user's MetaMask signature to generate a temporary decryption key, passes that key to the FHEVM, and retrieves the clear, Boolean results of the hint, which we then display as too high or too low. This full lifecycle demonstrates the power of FHE. This is the private guessing game demo.tsx file, the main React component that builds our user interface. It is the visible layer that orchestrates all the underlying logic. Instead of handling encryption or Ethereum communication directly, this component imports and consumes 3 crucial elements. First, the useMetaMask Ether signer hook handles wallet connection and access to the user's provider and signer. Second, FHEVM initializes the necessary FHE execution environment in the browser. Third, and most importantly, it connects to the usePrivate guessing game hook we just reviewed, passing it all the necessary state like the FHE instance and the wallet signer. The rest of the file is purely for UI and interaction. We use conditional rendering to determine what the user sees. For instance, we check if the connected wallet address is the contract's owner. If so, they see the game master controls for setting the secret. For all players, when they input a number and click Get Hint, the component takes that input and passes it directly to the powerful functions exported by our custom hook, like private guessing game.getInt guess. This design effectively separates the complex FHE state management and contract calls into the custom hook, leaving this main component clean, responsive, and focused entirely on providing a seamless user experience. To begin the client-side demonstration, in our terminal, we run npm run dev mock. This command launches the React front-end application in development mode and establishes the connection to the FHEVM environment. The application is now live and ready for a wallet connection to begin interacting with the secure smart contract. With the front-end running, the first step is to connect your MetaMask wallet. Okay, I will reload my website so we can use the wallet connect function again, which helps us sign the transactions. I've already performed the set secret transaction behind the scenes, using FHE to encrypt the number. Using FHE to encrypt the number, let's say 50, before saving it to the contract. Now, as a player, I'll make a guess. I'll try 45. When I click Make Guess, MetaMask prompts me to sign a transaction. This sends my encrypted guess to the contract. The beauty here is that both the secret and my guess remain confidential during the entire on-chain process. Let's check Etherscan for that transaction. If we inspect the input data for both the set secret and the recent make guess transactions, you only see long, opaque strings of ciphertext. Crucially, the public ledger and transaction logs do not expose the plaintext values. This opacity confirms the core security of FHE. The raw secret and the player's guess are never revealed on the public chain. Now we retrieve the encrypted hint. After clicking Get Hint, the contract returns encrypted handles. To see the clear result, we click Decrypt Hint. MetaMask asks us to sign a decryption key, which is passed securely to the FHEVM. We then immediately receive the clear hint. Too low. The game continues with full privacy intact.